Chapter 7 Gases, Liquids, Solids, and Phase Diagrams. Section 7.3 Fugacity. For ideal gas, its chemical potential is equal to its standard chemical potential plus RT times the natural logarithm of P over P naught. How do we get this equation? If we have a pure ideal gas, the chemical potential is equal to its molar Gibbs energy. And we know dG is equal to negative S dt plus VdP. When temperature is given, dG is simply VdP. If we integrate both sides, we have delta G is equal to integral of VdP. The integral of VdP for an ideal gas is simply the integral of nRT over PdP, which is nRT times the natural logarithm of P final over P initial. And then the change in the molar Gibbs energy is RT times the natural logarithm of P final over P initial. Let's assume the initial state is 1 bar, the final pressure is P, and then over here this is the difference between the molar Gibbs energy of an ideal gas with pressure P and the molar Gibbs energy of an ideal gas with 1 bar pressure. And we have this equation. And also we can rewrite this equation. P is P naught times e to the power of mu minus mu naught over RT. So this equation originates from this equation. For a real gas, we have a similar equation, very similar, except every occurrence of pressure should be replaced with fugacity. Fugacity is denoted by F. But what is the fugacity of a real gas? Fugacity may be viewed as the effective pressure of the real gas that directly correlates to the chemical potential of the real gas. And why do we need this effective pressure? It's just because in an ideal gas, there's no attraction or repulsion between ideal gas particles. However, between real gas particles, there is both attraction and repulsion, and they both affect the value of mu. To take that into account, we need to modify this equation. We need to replace P with F. And in fugacity, the attraction and repulsion between real gas particles is taken into account. Now, what is F naught? F naught is also 1 bar, but this F naught is slightly different from this P naught. So really, what is this F naught? F naught is the standard state for a real gas. P naught is the standard state for an ideal gas. If a real gas is in the standard state, well, we say its fugacity is equal to F naught, and F naught is 1 bar. Alright, we simply say, well, a real gas in the standard state has a fugacity of 1 bar. And when it has a fugacity of 1 bar, its pressure very likely is either greater than 1 bar or lower than 1 bar. Alright, again, it's just because fugacity is different from pressure for a real gas. However, under this situation, when P approaches 0, F approaches P. Why is that? When pressure approaches 0, that means we often have a very large molar volume, and that means we have a very long distance between gas particles. In that case, the attraction and repulsion may become negligible, and in that case, F approaches P. The fugacity approaches pressure when pressure is extremely low. Now we define the fugacity coefficient, gamma. Gamma is defined to be fugacity over pressure. Gamma is unitless. Note that the fugacity coefficient of a real gas depends on its temperature and pressure, because when we have different temperatures or pressures, they may affect the distance between the real gas particles, and in turn it's going to affect the attraction and repulsion. Remember, when we have a shorter distance between those gas particles, we have greater attraction and greater repulsion. When the distance is longer, we have less attraction and less repulsion. They do not cancel, and that's why this F is often different from P. Now, at very high temperatures and very low pressures, we know the molar volume is extremely large. In that case, the gas particles are very far away from each other. Then the gas behaves ideally or nearly ideally. And gamma approaches 1, F approaches P. The fugacity coefficient of a real gas can be calculated using this equation. In this equation, we have the natural logarithm of gamma on the left-hand side. On the right-hand side, we have integral of z minus 1 over p prime d prime. P prime is simply a dummy variable. I was considering using p here, but we do need to use this p as the upper limit for the range of pressures. So we need to integrate this p prime from 0 to p. That's why we need another variable, p prime, here. You may replace this p prime with x or tau. It does not matter. You will get the same integral. Now, what is this z? Well, z is the compression factor. Z is equal to PV over nRT. When attraction dominates, z is less than 1. When repulsion dominates, z is greater than 1. So let's analyze this Ln gamma. When the repulsion between gas particles predominates, z is greater than 1, and over here you are integrating a positive quantity, and therefore this integral is greater than 1. Therefore, the natural logarithm of gamma is greater than 0, and then gamma is greater than 1, F is greater than P. When attraction predominates, z is less than 1, you're integrating a negative number, a negative quantity, you will get a negative result here. Therefore, the natural logarithm of gamma is also negative. That means gamma is less than 1, the fugacity is less than the pressure. So let me repeat, if repulsion predominates, PV is greater than nRT, Z is greater than 1, the compression factor is greater than 1, the fugacity is greater than pressure. When attraction predominates, the compression factor is less than 1, and the fugacity is less than the pressure. And over here, it's just because in this F, in this fugacity, we include the attraction and repulsion factors. Now we prove this equation. Why the logarithm of gamma is the integral of z minus 1 over p prime d prime. For an ideal gas, the chemical potential is mu naught plus RT times the natural logarithm of P over P naught. For a real gas, we have a similar equation, except this P should be replaced with F, P naught should be replaced with F naught. P naught is 1 bar, F naught is also 1 bar. However, they are different. P naught is the standard state for a ideal gas. F naught is the standard state for a real gas. Now let's take the difference between these two equations. So basically we have the chemical potential of a real gas minus the chemical potential of an ideal gas, and then these two cancel. We have just RT times F over P. P naught is 1 bar, F naught is also 1 bar. F over P is gamma, so we see this natural logarithm of gamma here already. Now let's take the exact differentials of both sides. We have d mu real minus d mu ideal is equal to the differential of RT times the natural logarithm of gamma. For a pure gas, the chemical potential mu is equivalent to the molar Gibbs energy. Therefore, we have d mu is just dg sub m, the molar Gibbs energy over here, and it's negative s sub m dt plus v sub m dp. When temperature is constant, this dt is 0, then we have d mu is equal to molar volume dp. For a real gas, we have d mu real is Vm real dp. For ideal gas, this d mu ideal is Vm ideal dp. The dependence can be different. Now we're going to take the difference between these two equations. So d mu sub real minus d mu sub ideal is molar volume of the real gas dp minus the molar volume of the ideal gas dp. So we're going to copy this equation here and here from the previous slide. We had d mu real minus d mu ideal should be the exact differential of RT times the natural logarithm of gamma. Gamma is the Fugacity coefficient. Gamma is F over P. Also, we have d mu real minus d mu ideal equals the molar volume of the real gas dp minus the molar volume of the ideal gas dp. Now we have the right hand side of the first equation equals the right hand side of the second equation. We have this. Now we can integrate both sides from p equals 0 to a finite pressure p. And over here we have RT times the natural logarithm of gamma at pressure p. And over here, this is gamma at pressure 0. And over here, on the right-hand side, we just need to integrate this Vm real dp minus Vm ideal dp. Over here, we use p prime simply because we used this p for the upper limit of the integral. We somehow need to change this variable to p prime or any other dummy variables. Now if we look at this equation, realize this ideal molar volume is just RT over P prime. Alright, we're using P prime as the variable. So this is the ideal molar volume. But if you have a real gas, this is a different equation for a real gas, because Z is equal to PV over nRT. And for a real gas, therefore for a real gas, V is simply ZRT over P prime. And that's why we have these two slightly different expressions here. Over here we have Z, over here we do not have Z. But all other expressions are exactly the same, so we can combine this RT over P prime and this RT over P prime. We have P prime on the bottom, and RT does not depend on pressure here. We do not need to integrate anything. With respect to temperature, we can take RT out. Now we have this side. Look at this one. Okay, we can simplify this. When pressure is extremely low, the real gas particles are really far away from each other, so the fugacity is close to the pressure. Gamma is close to 1. This term is equal to 0. So we just have RT times the natural logarithm of gamma is equal to this integral times RT. So RT and RT cancel, right? RT and RT cancel, and then we have the final expression. The natural logarithm of gamma is equal to the integral of z minus 1 over p naught d 1 over p prime dp prime. Okay, again from here to here, we used two steps. I think I just divided the equation, the left hand side by RT, the right hand side by RT, and then this part is just 0, only because when P approaches 0, gamma approaches 1. It's just ideal gas behavior when the gas pressure is extremely low. Alright, now we have this equation. It's proven. Okay, we proved that the natural logarithm of gamma, the Fugacity coefficient, is equal to this integral. Now let's look at one numerical example problem, 7.3.1. Let's say the compression factor of a real gas at room temperature is a function of pressure, so we have this function of pressure here. Again, Z does not have to be a constant at a given temperature. Z often depends on the pressure, and you can tell when pressure is very large, usually the repulsion term starts to predominate and Z is greater than 1. But when pressure is small, usually attraction is predominant and Z is usually less than 1. Now let's look at this calculation. What we need to do is we need to just plug in this expression of Z here and integrate everything. So now let's calculate the fugacity coefficient gamma and the fugacity when the pressure is 10 bars and 100 bars. So what if the pressure is 10 bars? We just need to integrate this from 0 to 10 bars. The natural logarithm of gamma at 10 bars pressure is the integral of this is Z minus 1, so this one disappeared. And then we have 1 over P prime and then dP prime. Why do we see X here? It's just because for convenience we can define X to be P over P naught. So this is just X and this is X squared. It's convenient only because X is unitless. It's easier to deal with. Since X is unitless, this is unitless, this is unitless, and the upper limit is now 10 instead of 10 bars because X is from 0 to 10 here. Now on the bottom we were supposed to have P prime here, but since we have this, well, P prime is just P naught X and P prime is X P naught. We just need to integrate this. P naught and P naught cancel. We just need to integrate a function of X, which is right here. The remaining steps are trivial. You just get logarithm of gamma is negative 0.05 and gamma is 0.95. Fugacity is 9.5 bars. So that means at 10 bars, the attraction predominates. Alright, and then let's look at another calculation. What if it's 100 bars? We'll just borrow this function over here. It's just we just need to change the upper limit to 100. Now pressure is 100 bars, X is 100. Plugging all the numbers, we get 0.4, gamma is 1.5, fugacity is 150 bars. So over here you can see when pressure is 100 bars, actually gamma is greater than 1, fugacity is greater than pressure. It tells you that the repulsion starts to predominate when the pressure is this high. For a chemical reaction that involves only ideal gases, it's easy to write out its equilibrium constant. For example, its equilibrium constant of pressures is simply this. We have products on top, reactants on the bottom, XY on top and B on the bottom. And it's an ideal gas. We don't have to worry about the attraction or repulsion between gas particles. We're simply using P here. So this is P sub X over P naught. This is P of Y over P naught, P of A over P naught, P of B over P naught. We did take care of the coefficients, and then we write, at equilibrium, if we get this expression, this is the equilibrium constant of pressures. Given this equilibrium constant, we can easily calculate the standard Gibbs energy of reaction, which is negative RT times the natural logarithm of K. But if all involved gases are real gases, we need to make some changes. Actually, the only changes we need to make is to replace every single P with F, every single pressure with fugacity, P naught with F naught, the standard fugacity on the bottom, and over here this is the fugacity of X, fugacity of Y, fugacity of A, fugacity of B. Because P naught is equal to F naught is equal to 1 bar, they are just the same, but F of X and P of X differ by this gamma of X. Again, gamma is the fugacity coefficients. Gamma is F over P. So F is P times gamma. That's why we can write K of fugacities is equal to this K of pressures. multiplied by this expression that involves fugacity coefficients for x and y on top and b on the bottom. And again, for a real gas, there's attraction and repulsion. They affect the chemical potential of every single gas. And now we have a different equation for the standard Gibbs energy of reaction. It's negative RT times the natural logarithm of the equilibrium constant of fugacities. Again, the equilibrium constant of fugacities and the equilibrium constant of pressures are often close to each other. They differ by a factor that consists of all those gammas, those fugacity coefficients of x and y on top and b on the bottom. And again, over here we see a superscript naught here. It means standard state. And for real gases, it means every single real gas has a fugacity of 1 bar, not pressure of 1 bar. They have a fugacity of 1 bar. And given the standard Gibbs energy of reaction, we can compute the equilibrium constant of fugacities. So K sub F is e to the power of negative standard Gibbs energy of reaction divided by RT. By looking at this equation, you can see if all gases involved in a chemical reaction are real gases, we do need to take the attraction and repulsion into account. Remember, this G is H minus Ts, and H enthalpy is U plus PV, and that U does depend on the attraction and the repulsion between all those real gas particles. So now you can see why we need to modify the equation from here for ideal gases to here for real gases.